Previously, I've said that just because two sets have infinite cardinality doesn't mean that they have the same cardinality. Um, in particular, we've seen that when you're infinite, you could be countable, meaning your elements could be enumerated, or you may be uncountable in that you can't enumerate your elements. And we have a little bit of experience showing that sets are countable, but we haven't technically proven that a set is uncountable yet. So in this theorem, we're going to prove two really important facts. The first is that Q is a countable set, so the rationals are countable, and the second is that the reals are uncountable. So to prove the rationals are countable, there's going to be a key here to how we approach this. So to show one, here's the key. We want to group rationals in what I call finite chunks such that every rational appears in exactly one chunk. Then label the elements one chunk at a time. Now, what do I mean by this? To give an example of what I mean by chunking, recall that we were able to show that the integers have the same cardinality as n. So the integers were a countable set. And the way we did this, well, if you look at z and you write it out, the way we typically would list the values in this set would be according to the order, the size of the number. So we could say this is -2, -1, 0, 1, 2, etc. But we can't, when we go to label these, remember we didn't want to label all of the negative numbers at once and all the positive numbers at once, because if you do that, you've split your set into two chunks, the negative half and the positive half, and each of those chunks is infinite. And so if you require yourself to label one of those chunks before moving on to the next one, you're never going to get to the next one. So instead, what we did was we grouped our integers into finite chunks. We said 0 is its own set, and then ±1 is its own chunk, and ±2, and we basically just lined those up and then labeled them. So we said, okay, first let's label the chunk that contains 0. Then let's label the chunk that contains ±1. So I need to make sure I label all elements in that chunk before I move on to the next one. Etc., like this. And so here, these are finite groupings or chunks of the integers. And so the question is, can I do this in a way for the rationals as well? It's not going to be as obvious because the rationals appear much different. I mean, it almost is like there's more numbers in it, but remember, if we're saying the rationals are countable, ultimately that means that there are the same number of rationals as integers. And that's kind of mind-blowing if you think about it. So here's the sketch of the proof that Q is countable. So here's how we're going to make our chunks. The first set or first chunk I'm going to call A1, and that's going to consist only of the number 0. So far we're starting out very similar to the integers. The first chunk is just a set with 0 in it. Then, for n greater than or equal to 2, we're going to let an be the set that contains, it's going to contain numbers of the form plus or minus p over q, such that p and q are in n, with p plus q equal to the little n that you're looking at, and p over q in reduced terms. We know that there are infinitely many ways that you could represent the rational number 1/2, for example. You could write it as 2/4, 4/8, etc. For the purpose of creating our chunks, we're going to assume that the p over q that we have has first been reduced. And this is really important to make sure, for making sure that our mapping is going to be 1-to-1, in the sense that each rational number is only going to appear in exactly one chunk. So let's write out what some of these sets look like. So A2, for example, this is going to be all of the numbers that I can write as p over q, such that p plus q equals 2. Well, remember p and q are natural numbers. The only way to do that, I can either write 1/1 or -1/1, because I'm supposed to do plus or minus. The only way I can take two numbers, p plus q, and make them equal 2, when those numbers are natural, is to just use them both as the number 1. Okay, so this is my next chunk. Then A3, I'm looking for p plus q to equal 3. So that's going to give me the numbers 1/2, -1/2, and then 2/1, so 2, -2/1. And I'll write out one more. Here I want my numbers to sum to 4, but they have to be in reduced terms. So I'm not going to use 2 over 2, because 2/2 would not be a reduced format, even though 2 plus 2 is 4. And that wouldn't be good, because then I would be repeating the number 1, which I've already put in a different set. So this is going to be 1/3, -1/3, 3/1, -3/1. And so just a note here, 2/2, -2/2 are not in reduced form. So we don't include them here, even though 2 plus 2 is 4. And we just keep labeling like this. Now, take a look at these sets for a moment and ask yourself, do you believe that every rational number is in one of these chunks? Like if I were to look for the number 5/101, would you believe that there's eventually a set that it belongs to? Well, that would be taken care of by A106. And the fact that things have to be in reduced terms is guaranteeing us that we're going to have a unique representation of our numbers, such that all numbers will appear in exactly one chunk. And this gives us a way to line up our sets and label these chunks one at a time. And in that way, we're creating a first rational number, a second rational number, etc. So I'm going to first take A1, my first set, and that's 0. My next set that needs to be labeled is going to be 1/1, -1/1. Then I'm going to label A3. So that's 1/2, -1/2, 2/1, -2/1. And then I'm going to keep going, and I'm going to label the next chunk. So 1/3, -1/3, 3/1, negative 3 over 1. And in this way, I am labeling chunks of numbers. And I always know I'm going to move to the next chunk because each chunk is finite. So I'll always finish labeling one chunk and then continue to the next one. Now, how you label the elements within the chunks themselves is up to you. Notice I'm not going to... There's more than one way that you can enumerate the rationals. I could have sent 2 to negative 1 and 3 to positive 1, for example. This is just one way to do it. And so since each rational number appears in exactly one set an, and each an contains finitely many numbers, if we line these up and label our elements, we have a bijection. So let me write that down. Since each rational appears in exactly one set a sub n, and each an contains finitely many numbers, if we line up our sets A1, A2, A3, etc., and label all elements in each an before moving to the next set, so moving to an plus 1, we have a bijection. Now, I'm not going to write an explicit formula for this. As long as it's clear when you're making bijections and you're coming up with your labeling pattern, as long as it's clear that you're always going to get to every single number and you're only going to label that number once, then I'm okay as long as you demonstrate enough of the pattern. So because we have a bijection, this tells us that Q is countable. So in particular, Q can be enumerated. And this is going to be important. We're going to use this fact again later in this section. So in particular, Q can be enumerated. I could say Q equals R1, R2, R3, etc., where these are my rational numbers. So now we need to show that R is uncountable. And there are a couple of ways that you can prove sets are uncountable. For example, if you already know you have an uncountable set and then you show it has the same cardinality as another set, then that other set becomes uncountable as well. But one way you can do it is that you can suppose that you actually have a countable set. That its elements can be listed or enumerated, and list them out, but then show that no matter how you list them, there's a number that's been left off that list. And in doing so, what you've shown is that any enumeration of that set, so in this case the reals, results in some real numbers being missing, meaning it's impossible to enumerate all of the elements, and that means that it's going to be an uncountable set. So I'm going to assume that R looks like x1, x2, x3, etc. That all of these xi's that I have are exactly all of the real numbers. Every real number appears in this list is my assumption, and we're going to show that that leads to a contradiction. So here's how we do it. We're going to let I1 be an interval. It's going to be a closed and bounded interval such that we're going to leave x1 out of I1. So why am I doing this? What I'm going to do is I'm going to show that there is a way to use the nested interval property. There's a way for me to create a nested sequence of intervals such that each interval leaves at least, like each number in my list, my xi's, is going to be left out of at least one interval. Then I'm going to use the fact that the intersection of those intervals has to be non-empty using the nested interval property. What I find in my intersection is going to be that new real number x that we've left off the list. So given x1, for example, we have a number line. We know x1 is going to sit somewhere on it. You should believe that it's possible to pick your favorite closed and bounded interval that doesn't include the point x1. So let's say I put it right here. So this guy is going to be I1. I can continue this process such that I can now create a subset of I1 that I'm going to call I2, such that x2 gets left out of that. So imagine x2 was, say, right here. I could then create a subset, and this one would be I2. Now, it could be that when you go to create your set I2, it may be that x2 is already left out of I1, and so you don't even need to worry about excluding it. But the point is we can keep doing this where we shrink our interval, we exclude a single point, namely that the xn that we're looking at for the particular in we're constructing. And we keep going in that way, and then we're going to apply the nested interval property. So here, let I2 be a closed and bounded interval such that I2 is a subset of I1 and x2 is not in I1. And then we want to continue this process. And here you'll get I1 that contains I2 containing I3. So we get this nested sequence of closed and bounded intervals where each in is such that xn is not in in. So in doing this, what we've managed to do, if we come back up to our enumeration, we have guaranteed, sorry, that's my washing machine. We have guaranteed that each of the numbers we've claimed represent all the numbers in our enumeration of the reals is actually going to be left out of at least one of these nested intervals. So by the nested interval property, because I'm working with these closed and bounded intervals, there has to exist an x in the intersection of all of these in's. However, by construction, we know that x doesn't equal xn for any n, or for all of these n's, since xn is not in in. There's no way that x2, for example, could be in the intersection because x2 is left out of I2, so it's certainly not in all the intervals. And you can play that game for any value of n. So this means we found a real number. So we have found a real number x that wasn't on our list. That's a contradiction. We had assumed that every real number was enumerated in that list, but now we found a new number that we left off the list. Therefore, R is uncountable. And then, as I was saying before we started this proof, once you know that a set is uncountable, any other set A that has the same cardinality as the uncountable set will also have to be uncountable. And so recall, we showed that R had the same cardinality as the interval 0, 1. So 0, 1 must be an uncountable set. And what we'll actually see is true, and I'm going to demonstrate this in another video, is that any interval, regardless of whether or not it includes its endpoints, is uncountable. All of those sets have the same cardinality as R. And that's an important fact. So there are three main facts that came out of this video today. The first is that Q is countable, so its elements can be enumerated or listed. Second is that the reals are uncountable, and the third is that any interval is uncountable.